Hey there, this is a video covering factoring using the area model made just for Mrs. Taylor's amazingly awesome students. Full disclosure, I'm her daughter and I'm super nerdy and I love doing math and I love showing cool math things to math students. That's what I do. So I'll try to keep this video fairly short but detailed enough so that you have what you need to be able to factor using this model. So I wanted to start with a quick review of multiplying with area, which is such a fantastic way of viewing multiplication of polynomials with this area model. My colleagues and I really, really like it. And I just wanted to draw your attention to a couple of things about when you're multiplying. So typically when you're factoring, this expression over here on the left, that's what you're looking for. You're looking for the two things that are multiplied together that are going to give you the polynomial. And the better you are at multiplying, the easier factoring is. So in this example, I have two factors. I have a factor of 4x minus 1 and a factor of 2x minus 3. Now, when I'm multiplying with the area model, essentially I make one of those binomials the length of the rectangle. So we have 4x minus 1, and the other binomial, 2x minus 3, is the height or width, whatever word you want to use there. And this is a way of structuring it so that you are doing the distribution, but it doesn't look like traditional distribution. And so when I multiply them, I get 4x times 2x, and I would write the product right here. So 4x times 2x, I'd write the product here. 4x times negative 3 is here. 2x times negative 1 is here. And negative 3 times negative 1 is there. And so I would have 8x squared minus 12x. This is what, minus 2x, and this would be positive 3. And then what's really important to notice is when you're looking at the area here, that you have your x squared up here in the upper left, you have your constant down here in the lower right, and then on the diagonal, you have your two x's. Now, if you did a ton of multiplication like this, you would notice that it always comes out that way when you're multiplying binomials of this form. So you have the x squared upper left, 3, or the constant, in the lower right, and then on the diagonal you have the x's. And then to finish the multiplication, you would simply add all of those up, and so you'd have 8x squared. And then I think we're probably okay combining those in our head. Negative 12x minus 2x would be negative 14x, and then we'd have the positive 3. And so that's how you would multiply. So what we're about to do is to use this same model, but to go in the opposite direction. So we'll start with something like 8x squared minus 14x plus 3, and we're going to go back and find the factors, the 4x minus 1 and the 2x minus 3. So I wanted to draw your attention to that particular property, that is always how the rectangle behaves. If you don't believe me, write a couple problems on your own, do it out. You'll see that it always comes out that way. Now, the other thing I wanted to review is GCF factoring. And the great thing about doing the area model is that this is the only factoring you really need to do. Because you got to do a little bit coming up with the numbers, but GCF factoring is you're just looking for the greatest common factor. And so what I would have my students do when they're first starting GCF factoring is I would have them find the prime factorization. So 3x squared literally means 3 times x, and then I would change the color up here just to separate it for them. And then 15 factors into 3 times 5, and then you have an x. And then I'd have them look at those two groups, and that's why I separate them with a different color. So you can see, okay, we've got two groups. What do they have in common? And we see that they have a 3 in common. So we would say 3 is a common factor, but it's not the greatest common factor because they also have an x in common. And so the GCF here is actually 3x because that's the biggest thing they have in common. And so if you were factoring out the GCF, you would factor out the 3x, and then you can see what you're left with. You're left with the x, you're left with the 5, and of course you have the minus sign. Okay, and that would be your GCF factoring. If you have this one over here, we have 2 times x, and then 4 factors into 2 times 2. And so our GCF in that case is just the 2. That's the only thing that both factors have in common. So you would factor that out. And then you would multiply the x squared back together again. So x times x is x squared. And we have the plus 2. If you're wondering, like, where did you come up with that? X squared and the plus 2. So it's whatever's left over. So GCF factoring is essentially reverse distribution, and it can get pretty awful with lots of variables and very big numbers, but typically when you're factoring quadratics, it's not that bad. One quick note before we move on though, if you had something like 2x plus 2, and you recognize, okay, the common factor is 2, you would be left with a 1 over there. And a common mistake is to say 0 because you're like, oh, I factored the 2 out, so there's nothing left. But that's really a 2 times 1 over there on the right. So how does this play into factoring? So I'm going to go through 3 examples of factoring this way and kind of take you through the thought process. So the easiest kind is the kind where you have what's called the leading coefficient of 1. So the x squared there is really 1x squared, and that actually saves us a step. So you set up your area, your rectangle here, and then this is why I wanted to go right before. The x squared term is always going to go in the upper left, and your constant term is always going to go in the lower right. That's always going to be the case. The trickier part here is figuring out what is going to go there, and that's where you've got to maybe have a piece of scratch paper handy. It depends on how comfortable you are with the numbers, but essentially we are going to be looking for 2 numbers that multiply to 18 and add up to -9. So for some students, you can look at that and you will see it immediately. You'll look at that and say, well, that's -6 and -3. Other students might need to have something more methodical where they start listing the factors of 18. So you've got 1 times 18. If I add them, I get 19. If I subtract them, I get 17, but I'm not getting a 9. 2 times 9. If I add them, I get 11. If I subtract them, I get a 7, but I can't get a -9. Then we have 3 times 6, and we have a winner. So if I add those together, I'll get a 9. Now I don't want a 9, I want a -9, which means that what we're dealing with is -3 times -6. And you might want to do a quick little double check on that, just make sure, like, yes, those multiplied at +18 and they add up to -9. So once you have those numbers, then you put them over here in the rectangle, and it honestly does not matter where you put them. And I'll show you that. I'll just kind of do the problem out over here and just show you that that's the case. So if you're wondering, well, why didn't she do this? Well, the answer is I could have. Okay, so once you have the 2 numbers, you just put them into the other 2 slots. And then here's where the GCF factoring comes in. Pick any direction and find the GCF. I would pick the easiest direction that is subjective. So you could look at these 2, do x squared and -6x, find the GCF of those 2 and write it up here. Or find the GCF going this way, the greatest common factor of x squared minus 3x, and put the GCF here. Or find the greatest common factor this way, or find it this way. Just look at what you've got there and see what's the easiest GCF to find. I would strongly recommend using the x squared as one of them. So I wouldn't necessarily recommend doing this one. And if you have the option of avoiding a negative, take it, but really any of them work. So I'll go this way here. So we've got x squared minus 3x. This is x times x. This is -3 times x. So my GCF is x. And here's the brilliant part of the area model is you're actually done with your factoring. The rest of this you can do with multiplication. It's pretty awesome. So to figure out what goes right here, you would say x times what would give me the x squared? Well, that would be another x. To figure out what goes here, you would ask yourself, x times what would give me that -3x? That would be -3. And to figure out what goes here, you can do either x times what gives me -6x, or -3 times what would give me positive 18. The answer to both of those questions is -6. And what's another great thing about this is you've got this instant place where you can check your work. And so you can do a quick little x times x is x squared. Yep, x times -3 is -3x. X times -6 is -6x. -6 times -3 is positive 18. And then just don't forget that your answers are actually the length and the width, or length and height of the rectangle, and there are your factors. Now, if you put them into the rectangle the other way, it actually comes out exactly the same. So you could factor this way. Okay, the GCF between x squared and -6x is x, and then you would fill in the rest of this. So what times x gives me x squared? X times -6 gives me the -6x, and this is the -3. And you notice that you get the exact same dimensions. You get one of the dimensions is x minus 6 and the other is x minus 3, but it doesn't matter what order you write your factors in because multiplication is commutative. So just like 3 times 5 is the same as 5 times 3, you can switch the order. You can do the same thing here. It doesn't matter which one of those you write first. So you'll get the same factors either way. All right, second example is a little bit trickier, and that's because we have a leading coefficient of 2. It changes one step in how we do this, and it might be familiar if you've done factoring by grouping before. So we have 2x squared and -7. So the x squared upper left, constant in lower right. Here's the additional step. You can't, there aren't two factors of -7 that add up to -13. So that's a little problematic. What we need to do is multiply the a value and the c value. So we'd have 2 times -7, and so the number we're going to play for there is -14. So we're looking for two numbers that multiply to give us -14 and will add up to give us the -13. If you have trouble remembering that, just remember that when we find them, we would add these together. We always add. Again, it goes back to the multiplication. So again, some of you might just, you'll look at this and say, I know what that is. It's -14 and +1. Others might need to be a little bit more strategic, but if I do 1 times 14, I can get a 13 out of that. I can get a -13 out of it if the 1 is positive and the 14 is negative. As before, it does not matter where you place them in the box. So you can pick either rectangle, and then you just have one GCF step to take. I like this direction because I can see that the GCF of 2x squared and 1x is an x. And so x comes out, and then I don't have to do any more. I can just ask myself, x times what would give me the 2x squared? Well, that would have to be a 2x. X times what would have to give me 1x? That's got to be a 1. And then 1 times what would give me -7? That's got to be -7. And you could use the last one as a check. Does -7 times positive 2x equal -14x? Why, yes, it does. And so you can just do that quick check. All of the boxes should work. And so our answer is x minus 7 times 2x plus 1. Ta-da! All right, last one. That is my cat that you're hearing. So this is maybe the most difficult version. I don't know if the program you guys are working in, I think, is a bit notorious for giving some awful numbers, but hopefully this will cover it. So we have 12x squared. I look at a leading coefficient of 12 and I kind of think, can I do this a different way? But we have the 12x squared that's going to go in the upper left, and we have a -2 in the lower right. And then we just have to figure out, how does that -5 break up? So as before, when you have that leading coefficient, you do need to do the multiplication. So we'll do 12 times -2 is -24. So that's the number we're looking for. And we're looking for two numbers that will add up to the -5. So if you know it, awesome. I'll just go ahead and list them. So 1 times 24 is, I can get a 25 or a 23, but not a 5. 2 times 12, I can get a 14 or a 10, but not a 5. 3 times 8, I can get a -5 out of that. if the 3 is positive and the 8 is negative. And then my last combination is 4 times 6. Sometimes it's good to check because you can get a little tangled up with the pluses and the minuses. It doesn't happen all the time, but it can happen. And 4 times 6 does not give me a 5. So I've got my positive 3, and that'll be a positive 3x, and I have my negative 8x. And so there we go. Now, GCF factoring, looking at this the way I have it set up, this is my direction that doesn't have any negatives. So I'm going to GCF factor in that direction. Greatest common factor between 12x squared and 3x is indeed 3x. And then the rest of it's multiplication. So 3x times what gives me 12x squared? That would be 4x. And 3x times what gives me 3x? So that would have to be a 1. And I'm going to kind of avoid that, but 1 times what gives me negative 2? That would be negative 2. And then I'll use this one as my check. 4x times negative 2 is negative 8x. And again, all 4 multiplications should work. And there are my 2 factors. So this is 3x minus 2 times 4x plus 1. I think this is a great way to do it. It minimizes the amount of factoring. It's a great visual. It'll support your multiplication. And for those of you that go that far in math, when you get to polynomial long division, there is absolutely no better way to do it than modeling it with area. So I hope this video helps. Sorry I ran long. It's kind of what I do. I get really excited about it. This is how I nerd out. And hopefully you find it helpful.